guys, my name is Tianhao and I'm a graduate student in Professor Otis group. And today I'm going to give you guys an introduction about the AFLOW-CHULL part. So, so first of all, I want to make sure that all the audience can see the screen, like the text, the word very clearly. So the folks in the backline, are you guys able to see the screen over here? All good, all good. All right, perfect, perfect. All right. So at the beginning, I still need to you guys to navigate to the s4e.ai, this website, and to click on this 03 AFLOW-CHULL part. It will direct you to the collab for this child section. So if you click on this part, you will just go to this very nice collab over here. Yep. Alright, so welcome guys. So this section is about the introduction to for the AFLOW-CHULL, and AFLOW-CHULL is a mode for the AFLOW++ software that which is enable us to make a prediction of some compounds, which is very efficient, is extremely powerful, and with adding some extra options and flags, it will give you a lot of freedom to do a lot of work. So start with the content, and I'm going to give the introduction like this way. So first is the installation of the AFLOW and some setting up for the environment, and then I'm going to introduce the AFLOW stuff. And following, I will give you the hands-on introduction of how to use AFLOW with these kind of options. And then we have like some little exercise. We have a brief introduction of the AFLUX-OPEN. We'll talk about later. So let's start from this part to install the AFLOW and the environment packages. So I made a comprehensive cell over here. So if you just click on this button, it will just run this command automatically, as you can see. So this little green symbol indicating that it is unzipping the AFLOW publication zip file. It will take some seconds, but yeah, give some time. We are unzipping the file. We change the permission to the file. We change the path. And we are making the PDF reader, which enable us to read the PDF report later. It'll take a sec. Alright, it's done. So if you're finishing up, let's do some tests of these functions. So first of all, let's do the test for the AFLOW package. So if you can see the declaration like that, it means that you are successfully installed the AFLOW package. So if you click on this button, it will show the symbol of our lab, S4E. So that will be able to let us to read the PDF file. If you can see this symbol, it means that you can already successfully install this Python library as well. So for now, we just finished the AFLOW installation, and this is the beginning of this AFLOW-CHULL part. So I want to ask you guys a question that. Is there kind of a scenario that you're wondering some materials, are they able to form? Like you're doing a project, like there is like compounds A, B, or B, C, or A2, B3, like that. So you're wondering, is able to synthesize? Can I use this material in the real life? Is that able to exist? So probably you are supposed to look through the website. You are supposed to go to the library to read some like dictionaries, references, and take hours and hours to find out, oh, it is able to synthesize, or otherwise, probably there are it has not been reported yet. So in this kind of situation, AFLOW-CHULL is able to let you to know the stability of this compound very easily with just pushing one button. So, without any information of this package, so I just want you to use this command. Click on this command, and you will get a report for this example system. So if you click on this button, it will just grab the data from the database and to calculate and make a very nice report. So you do not need to know the log information over here. You even do not need to know how this command works. You just need to simply push the button and you can understand what is going on. All right, so we are finishing creating a report for this system. So if we just click on this button, we will see this is the report we just obtained. So let's open up this report and see what is going on inside of this report. So you can download this report to your local computer, and you can also run this command to let it show online. So I just choose to let it show online. So if you look at this report, you'll get the first page is a plot. It's kind of with so many dots inside, with some like lines, timelines, with some concentrations and energy. It's kind of confused, I know. So following up, there are some tables, kind of a summary with some tables for the binary, different compositions, and different compositions, and following with the unitaries. So it's pretty confused. What kind of report tell us? What kind of information that report tells us? So we will go through this report right now together to explore. So for the very beginning, this report I just divided into two parts. The first part is the plot. At the very beginning, the first page, the plot. So if we look at the axis of this plot, the y-axis is the formation MeV per atom, and the x-axis is the concentration. So from the left to the right is from the pure PD to the pure SE. So if you in the middle of this concentration, so there will be a PD SE which is 50%. So that is very clearly and very easily to understand. And there are also some dots on this figure, as you can see over here. They are colored with orange to blue. There are some like X, and there are some circle over here. So what are those dots means? So if you look at this column, so they are in the same. This column of data sets are in the same concentration, which is like PD1 SE2. So that is the 66.7% of the PD. Actually of the S. It should. I mislabeled that, but it should be like the concentration of the PD and concentration of the SE. So in this same column with the same x-axis, so there are different formation entropy. So these dots in the same concentration represents the material with the same concentration, but with the different structures. So just like the previous section held by Shell, so we decorate the prototype with the elements. For this scenario, we decorate the prototype with the PD and the SE, and they have the different structures. And therefore, if we are going to calculate this kind of different structure, we are going to get the different energy from the DFT calculation. So this is the formation of this column of data sets onto this hull. So I'm going to introduce how do we plot this hull. So as you can see over here, we have like 352 entries for this hull. So they just distribute randomly, and not randomly, they just distribute based on their formation entropy and the concentration in this figure. And how do we plot this hull? So for this cost hull, I want to just introduce some basic understanding of the thermodynamic knowledge. So give us an equation that it will tell us if this kind of material goes to decompose or maintains in their original state. So let's say the free energy equals to the entropy minus the entropy times the temperature. So in this scenario, for our study and research, we do not consider the temperature because all the DFT calculations are done under the zero temperature scenario. So literally, we just only consider the formation entropy part. And the formation entropy is calculated by this formula, which is based on the entropy of every component of these materials. So this formation entropy part already been calculated by when we are doing the DFT calculation a few months ago, and the data already been uploaded into our database. So the lower of this formation entropy means that if you're going to form this kind of material, it will release the heat. It will be more stable than their pure components because it will just release energy. So we can see the less of the formation entropy, like probably like till 100, like 200 or 300, the more stable this kind of material it will be. So we just mentioned we have like hundreds of the materials, like they just decorate with the different prototypes, which means they have different different structures, and we calculated for these different structures with different concentrations, so we can get like different formation entropies. So AFLOW-CHULL will grab this kind of hundreds of entries, the information, and to plot this kind of figure. So they just distribute the entries with their corresponding concentration and formation entropy into this figure and find out the entries with the lowest formation entropy. You can see there is a line right here. Basically, AFLOW-CHULL will pick up the lowest information entropy part and add them together to form a cost hull. So in this kind of situation, the data point on this white line should be the most stable one because they have the lowest formation entropy. So this tells us in this scenario, PD4SE, PD7SE4, PD17SE14, etc. are the most stable materials. And there are some extra stuff I want to tell you guys because so if we look at this figure, so if you really want to know a particular concentration for a material, that if this material is if this is stable, and if that is not stable, what kind of stuff it will decompose to. So you can look into this figure. So let's say, for example, the PD2SE3. So it will corresponds to the concentration of 0.6 over here, and you can notice that it is not on the hull, and probably just some few MEV atom above the hull means that is not stable. This material will decompose to the most stable components on this facet. So it will decompose to the PDSE and PDSE2 over here. So the distance from this data point to the facet, we call it the distance to the hull. So this distance to the hull is kind of the driving force that indicating how likely this material is going to decompose into these two stable materials. So, as mentioned by Professor Ozis in the morning presentation, the room excitation temperature energy is like 25 MeV per atom. So if the distance to the hub is within the 25 MeV per atom, it's likely to be stable. But if that is about 25 MeV per atom, it says that this is most likely is unstable. So if we look at right here, so this concentration of material will decompose into the 0.5, 0.5, and 0.33, 67. So the distance power is like 63 MeV per atom. That is about the 25 room temperature criterion. So this is basically what this kind of accounts tell us from the first page, from this plot. So you can easily have an understanding of what kind of composition of this material will be stable. So just at this timeline, this the data set on the line, so it will tell you directly. So if you are going to look through these tables in the following pages, so you will like have more understanding of that. So what are those summaries? What are those tables? If you we just pick up a table for the PD5SE as an example. So the first column is the prototype, which is the structures, and the second is AUID, and the AUID is just kind of the unique ID for every entries in the database. It is kind of like the SSN for every citizen. So the third and the third and the fourth column is the space group, and then the space group after reaction. We really care about this part and this part, which is the formation entropy and the distance to the hub. So these two parts really tell us is this material going to be stable or not. Yeah. So there is also a ground state, which is the stable table. So as you can see, with the same concentration, they have different structures, and for this structure, it should be the stable one because the distance to the hub, is 0, and it has a relatively low formation entropy. So that is the table tells us. So if you want to look through like what is the material, what is the structure of this PD4SE in the PDF report, you just need to click on this data site, and it will just directly lead you to the summary of the lead you to the table of the summary. So I can show you guys if you download this report and you back to the. Yeah, so if you click on this data set, you will just need to go to this point. Yeah, so it will tell you, oh, we have concentration in this place, and the structure is like that. It will be stable. So, so this is basically the plot and the table of the whole report. So now I can see you are able to report and understand the information inside. So this is basically the workflow of the AFLOW. So I believe Professor Otis mentioned that in the morning as video, but I just want to make sure that you understand that topic. Yeah. So you feed the AFLOW-CHULL with hundreds of data sets with the same system. Let's say the PDSE. So AFLOW-CHULL will grab the data from the from the database and put the data set over here. So next, the CHULL will think. So if there are any data sets outside of these three timelines, so if there is some point outside, the CHULL will automatically to recognize which is the hottest, which data set is at the outer layer of the it is the hottest. So it will connect this point with the hottest one to form a new visit. So which means it will move this green line into this way. So by doing this, AFLOW-CHULL is able to maintain that all the lowest energy data sets on the timeline on the facet. So it will repeat for us for some cycle to do the experimentation, and finally we can make sure that the child can cover all the data sets, and all the data sets on the Hopkins hall is the most stable one. So like the plot over here. So that is the AFLOW-CHULL algorithm. So our example before is about the binary system. So actually, the child is working for is able to work for the multi-component system as well. From the ternary, and it is also able for the quaternary and the factory as well. But as long as it's about the ternary system, we just cannot draw the figure from that. But anyway, I just want to show you another example for the ternary system. So if you click on this button as well, so AFLOW will grab the data from the database. So we are using the unary system like AG, AU, and CD, binary system AG, AU, AG, CD, AU, CD, and all the channel system AG, AU, CD to populate the hub. So as you can see over here, we are using like almost like 1,000 data sets to populate the hub. So you can get a very nice picture. Give it a sec. Because there are so many interests that AFLOW-CHULL is supposed to get. So it will take like a little bit longer than the AFLOW-CHULL for the binary system. So we can have the report over here. Well, we have the report over here, so I just download that. Now you can also view the report over here by clicking on this button. So if we open the report, so this report is pretty similar with the binary report, but for the Hopkins hall, it's kind of a three-dimensional visualization, but it is not. It is a wire good to see over here. So the color from yellow to the blue is from the higher information entropy to the lower information entropy. So it's kind of there's a dimensional stuff. I will show you later on the website. The website has a very good interactive features in that. So by making the connection of all the lowest energy, we can have these timelines, and for example, these two ternary systems are on the bottom of the hub, so they should be the most stable one. So if we look at the report over here, we can see that this AG4 AUC is not stable, and it is not on the hub. So AG2 AUC is stable, is ground state. It has a distance without is 0, which makes sense, and the frequency is negative 112. So we have another ground state, which is AGU2 CD as well. So this is very easy to read the stability. So I want to show you the website, web application of the AFLOW-CHULL, because if you click on the button over here, so it will, let's go to the AFLOW website. So the AFLOW-CHULL website application can offer us a very good visualization feature. So let's see the AG and CD and AU. So we click on this, and we can get a very nice plot over here. As you can see, if we just look that from the above, we can get a very similar plot, just like we have in the report. So yeah, this one. Yeah. So basically, this is just a different view of this hub. So if you turn this hub into another way, so you can see that the different interests and the different energy, probably they are positive, probably they are negative, and there are probably few interests just sit on the bottom, So if you click on these hard points, it will only show the points which are set on the hub. So in this scenario, we have for the ternary system, we only have AG2, AU1, CD1, and we're supposed to have one more. But I'm not sure where. Yes, this one. Yes, so if you click on this entry, it will give you the information of this entry as well. Yes, so for the AG, for the ternary system, AG2, AU1, CD1, it tells you what kind of prototype it is. That means that what kind of like structure it is, for the energy, the density, the stability, radiation, the N+1 as begins. All of this information that you can obtain from this website application as well. I personally like to use the website application for the ternary system because it will be more fun to play with this interaction feature. So this pretty much that. This is also works for the binary system. If you try to reset and use for another system like UGC, it will probably take a while to load. We'll just leave it here. So by doing this, I believe that you can solve the question that if this material is going to be stable. So in this case, whether you have a new material or just you have some like planning for some particular system, you can use the AFLOW-CHULL to solve this question. This material is stable or not. So following up, I want to introduce some options for the AFLOW-CHULL command as well. So the default, the AFLOW-CHULL will output the PDF file which is highly readable for the AFLOW user. But there are also some other formats that you can output with. For example, you can use some like TXT file. You can use some JSON file as well. I will talk about later. So the first point I want to show you that there is a way that to hash code generate the how for a series of systems that you are interested in. So for example, let's say if we use this command, LA equals to LI and A and the semicolon O and IDIES. So this command will give us a combination of these two parts. So it will command the LIO, LIS, NAO, and NAS. So in this scenario, you just need to push this one button to generate like 4 house. And you can do more actually. You can just put like a list of like cations over here, a post of like anions over here, whatever kind of elements that you are interested in. So with pushing this one button, you can like you here, you just take a coffee, you have a snap, you take a fancy dinner, and then tomorrow morning wake up, you can get a tons of the house for the systems. So once you get this report, it is very easy to grab the information from this report. So just like I said, you can choose to make the output file into the JSON file, and from this JSON file, you can grab the stable materials from this JSON file with some very easy Python script. So I already include some JSON file here. So how do we grab the information from some stable material? So just push this single button, and you can get like for which kind of compounds and what kind of structure it is, and what is this new ID. So this will be the stable material of this system. So it is very easily access the result, no matter from the PDF file or JSON file or TXT file. So you just need to do a little bit of post-processing to grab the information that you want. You can also grab the energy from each materials, each entries. It is pretty easy to use this kind of edition on the present screen. So, as mentioned, AFLOW-CHULL is able to make the output file into the specific format. So, if we do not use this flag, like we just use AFLOW-CHULL, LO equals to what, it will give us a PDF file. But if you specifically I want the JSON file with the flag --print equals to JSON, it will just automatically give a JSON file. And if you also want a PNG, like a picture or a TXT or PDF, you can just simply add a semicolon and add the PNG. So AFLOW-CHULL will know that, okay, this guy wants JSON file and PNG file. So it will generate two files simultaneously. And you can just add more if you want text file, PDF file. You will click on this button, it will give 4 files in one time. So you can also ignore some data points by using the --inlet plus the UID of this data point. Because probably you or you can use bind as real. So this real just remove the data point on the how. So I guess the way that we plot the figure that without the 15% point for understanding the stability criterion is using this feature. So there is also a command to understand all the flags and options for the child. So you can play with it, and there are so many options. There are so many features for this default child. So you can no documents, use documents only. You can do the include all the layers and everything else. So this is pretty much of the usage of the AFLOW-CHULL, and I now have some exercise of that will be very easy to work with. So you can use the web page application for the child, and you can also use the command line over here. So if you're going to use command over here, just simply click on this cell and use the command. We start with the symbol and then AFLOW stuff, whatever it is. So I will set up some 15 minutes for you guys to finish up these questions. So I already listed these commands previously, so you can check it out, and it will be easy. So let's see. If you guys have any questions, just raise your hand, and my colleague will come to you and solve the question for you.
Two general questions.
Yeah.
First one, if the material I want to synthesize contains more than 3 components, can I also use this AFLOW-CHULL?
Yeah, just like I said, so AFLOW-CHULL is able to work for the 3, 4, 5, 6 multi-components as well, as long as we already have the calculation for this 4 or 5 or 6 components system, because we have the unary and the binary entries for construct such kind of a material, but we also need to at least calculate the data set of these 4 or 5 or 6 components to let it set up a how. So it is able to work, but we just need to do one more calculation for the material that you're interested in.
Second question is that if the material I would like to synthesize contains non-metal, so all the component in my materials is non-metal, can I use this AFLOW-CHULL?
You are seeing
so for example, I have 3 components like silicon, oxygen, and fluorine. So can I also use this AFLOW-CHULL?
Yeah, I would say you can use that. You are able to use that, but probably there are some. I'm not saying error, but it's not that accurate because for the DFT calculation, for the metal is the DFT is working very well, but for some the iron, like the fluorine, the iodide, the oxygen and sulfur, it probably needs some correction on that. So we have application which is AFLOW-CCE. So we already did some work on that. You may check it out. So we are currently working on that as well to make sure for the prediction for this kind of material contains non-metal elements is as accuracy as possible. But overall, yes, we can do that, but it's not that. It is relatively reliable. Yeah.
What does the dash force do?
Yeah. So.
How does it bypass?
Yeah. So for example, if we are going to generate the Hall for some particular system, but we do not have enough data sets. So which means probably this concept will not converge very well. So in this situation, the AFLOW-CHULL will give you a warning that we do not have enough data set. Probably this prediction is not that accurate. Are you going to still plot the field in that one? So you can just add this force option to make it force it to plot the const Hall for this system.
Okay, but then what physics does it break to give the answer? Like if I used dash force, if I didn't use it, it was stopping at some point. But then if I add the force and then I run it, so what is it? What's the error that it's considering, and then is it just the data set or something else?
Just like I mentioned, so probably you can have you're not able to have a quantitative analysis of this system, but you have an understanding of which kind of composition and it should be stable. So I have a example for you. So if you look at this figure, so actually. So for the figure A and figure B, these are the same system from different database. So for the figure A, as you can see, there are so many binary systems, and for the for the figure B, as you can see, there are so many ternary systems, but they don't have so many binary systems as the figure A did, right? So if we do not have enough data sets to probably the Hall, the shape of the convex Hall, like the lowest deformation recipe of this composition, probably it will not be so accurate. But it still will have a sense that this kind of composition, like probably 50-50, probably like 33 and whatever it else, it probably will be the stable one. But probably there are some another data sets which is not explored yet, probably below that as well. Are probably above this as well, but just within a very small range. So you are still able to use the dash force to understand this system, the stability of this system, but you probably do not. But you probably are not supposed to rely on these analysis totally. You are supposed to populate this Hall with more interest, by doing more depth calculation to make it converge.
So it's just little amount of data sets. It's nothing else.
Yes.
Question about the exercise.
Yes. Go ahead. Yes.
Yeah, there's some
the tab. Looks like it's trying to fill it out for you. Hit the tab. You see it? Hit the tab. Alright, go there. Look, it's filling it out for you.
It's wrong.
What's wrong?
Yeah, it's wrong, so I just here.
We're gonna let the whole energy. Fix the whole energy. Oh, I see, I see. I think it's AI.
It's kind of GI.
Or did you fill it in already?
No, so Google has like a AI assistant, which is like GI now. Already should be this like file sheet for what you know kind of.
So we can answer that question.
Yes, it is. I think that is just an assumption that I'm not AI, so.
That's kind of scary. I didn't have any confidence. Actually, you're right. The whole energy was wrong. But it was not that wrong. It's scary, actually. So it figured out the pattern. It's amazing.
Alright, so let's go through this exercise together. So we'll start with the first question. So what is the distance of the AL17CO12 from the hub? So you can use the flag with the distance to hub, but I prefer to read the report because the report can tell you everything basically. So let's open up the report of the ALCO hub. Download that. We got the report over here. We open up the report. So in this report, as mentioned, every composition is shown in the table, shown on the table. So we just look through the tables, find out the AL17, right? AL17 and the code 1712. Yeah, so this is the point that we want to learn. So this is like AL17 and the code 12, which is unstable. So the distance to the hub, according to this report, is 243, which is exactly the distance to the hub. So this is the first question. You also can use the UID with the flag of distance to the hub to get the data as real. So the UID is AFLOW, EF, whatever else. So you can just add a flag with D2H equals to the AUID over here. So it will just returns you the distance to the hub data. So for the second one, what is the stability criterion of the AG and MG? So as real, we just first generate the hub for this system, AG and MG system. So we download this system, we configure this system, and we open it up. So we look through all the compositions, we find out what's the desired composition. AG17, MG45. Yeah, over here. So as you can see over here, this trace is stable, is in its ground state. So the stability criterion can be obtained by this over here. So delta H stability criterion is 0 MeV per atom. So we can easily obtain by the report. Like basically every kind of property you can see from the report. So for this one, what is the energy of the ES, CR, and VHAL and the particular composition of this? So to solve this question, we can use the command that is the as usual AFLOW. You tell that we are using the AFLOW software, and you are telling the AFLOW that we are using CHULL part with the alloy, and we are going to explore the alloy of the AS, CR, and NB. So we need to add one more flag, which is Hall energy. So this Hall energy should be following first. It should be following the alphabetical part of the arrangement of the metal, the names of the metal. So in this case, AS should be the first one, CR should be the second one, and NB should be the third one. So if we put over here, the concentration for the AS is 50%, so we put like 0.5 over here. So for the CR is 25%, we put 0.25 over here, and that's all. Because AFLOW-CHULL is able to recognize the NB concentration should be 1 minus the 0.5 and 0.25. So by this way, if you click on this button, you can get Hall energy within this cell. Give it a sec. Yeah, it's getting some entries. So 900. Yeah, so as you can see right here, the Hall energy is minus 443. So this Hall energy is kind of the formation entropy plus the distance to the Hall. If you look through the report, you just plug these two data together, you can get the Hall energy like that. So this is the third question. The fourth question is that what ternary compound has the highest stability criterion on this NPT PB hub? So similarly, we just run this command and we can get a ternary system report over here. We download that. Yeah, so as you can see, we only have 2 ternary systems on the hub. So we click on this one. So we have this MN4 PDPT that is not stable. We just ignore that. We have MN2 PDPT which is stable. The stability criterion is 33 MeV over here. And another stable one is MN-PDPT2, which the stability criterion is only 1 MeV. So in this case, the highest stability criterion is for this system, M2 PDPT. So this is for the question 4. The question 5 is that what binary compounds are on the ALCR, ALM, and ALFE hub? That actually, I want to run this command because it should take a longer time because you can use the command like that, like AL and silicon with the CR and FE. So AFLOW will automatically generate the 3 cost hub for these systems. And you can use the Python script before, like I showed you guys previously, and you gotta grab the stable binary compounds, and that is very easy. So these are all the exercise answers. I hope that is works for you. So now you guys are able to use AFLOW-CHULL, probably, yeah. So this is for the AFLOW-CHULL. So I also want to introduce the AFLUX-OPEN to you guys, because there is a very good question from the audience. So as this question before asked before, so if we have like a 4 component system that we is not in the database, so how should we deal with that? So the first is that we just simply create the postcard and the postcard like for the data calculation and feed it to our database, and then we can plot the cost hub gain within this interest in the figure. So the second one is that probably all the work, there are some institute or there are some like university has already calculated has been already calculated by some institute or university. So which means that we can probably negotiate with them and use a tool that grab the data from their database and to populate into the cost hub. So we have this tool which is AFLUX-OPEN. So try to think. The AFLUX-CHULL is my mom. So I was like, hey mom, I want kind of like a fried chicken. So can you make me a fried chicken? So yeah, my mom said yes, I can, but I did not have the chicken and oil and like onions to make the flavor of that. So how should we do that? So my mom placed an order on the Instacart from the Walmart, from Amazon, and from the Costco. So this platform, this Instacart is kind of the AFLUX-OPEN. And the Amazon, the Costco, and the Walmart is from the is like a different university and different database. Because let's see, so we have like S4E lab, we have our database, so we are the Walmart, and for the AFLOW, they are probably in Duke, so they are the Costco. So probably they are another like random university holds some data that which is not exist in our database. So they are probably like Amazon as well. So my mom, which is Chow, placed order from the Instacart, which is AFLUX-OPEN, and AFLUX-OPEN will tell this like 3 platform that hey, we are going to order this stuff. So these 3 organizations will provide data to the AFLUX-OPEN, and AFLUX-OPEN feed the data back to the AFLOW-CHULL. So Chow can generate the new cost hub to give us a better prediction for the kind of system. So this is the workflow of the AFLUX-OPEN, but I just mentioned that before. So as you can see over here, so for the AFLOW org, they only have some binary system for this CE/CDO system, and for S4E AI, which is us, we only hold some like ternary system for this CE/CDO system. So if we just build upon our database or upon their database, so we are not able to get a very good a very accurate cost analysis. So if we are able to use AFLUX-OPEN to combine these two databases together and remove duplicates, so we can get a more accurate cost and make sure that the how is converged. So that is the what is AFLUX-OPEN doing. It is also able to save the time for the researchers to do their research. So AFLUX-OPEN is also able to ensure the data privacy. Let's say if you order from the Instacart, there will be an order summary that at like 2024, like May 29, you order a chicken thigh from the Costco. So it will know that the chicken thigh from the Costco. So in that way, the institute, the company, or some university will have the credits for their data. So child knows this data is from this university. My mom knows the chicken thigh is from the Walmart. And if this data is very good, and I was like, hey mom, this chicken tastes very good, so I will give the credit to the university or institute. That is the first time that achieve this kind of data privacy, which is a big step of this data sharing federation infrastructure. So that is pretty much what AFLUX-OPEN is. So with the implementation of AFLUX-OPEN, we are able to make sure to predict, to generate the stable, the accurate prediction for some systems. That is the strength of this tool. So this is pretty much of this section. So if you guys have any questions, just feel free to ask me.